So this video I'll be going through the 2018 end of year electronics exam. I'm going to just be looking at the questions relating to the basic principles type questions and digital type questions. I'll be ignoring any of the analog electronic questions. You should always read the instructions at the start of the exam. So you can see here that you write in the places provided, things like that. So sometimes these instructions change from year to year, so it's pretty important that you make sure you read them. Sometimes they add additional instructions as well. So these are, in this case, related to how to give numerical answers and how to use answers that are given by the examiner. So show that type questions and how to work with those. So if you, in this case, show that type question, it would probably give the show that the answer is about 1.2 or something like that, and then you give it to one extra significant figure. So maybe 1.22 would be the correct answer that you might calculate. So that's how you record it. If you aren't able to find that for some reason, so either you don't know how to do it or your answer isn't seeming to come up with exactly the right one, you don't go ahead and use your answer. Use the one that's provided for you if there's further questions that rely on that answer. Usually indicates here that there's also spare diagrams and where they're going to be found. Okay, so this exam is split into two sections, or two parts. Is booklet 1, which is criterion 1. So section A is going to be those questions, and so question 1 is an amplifier. So this is related to analog electronics. I'll skip over that. Question 2 is a basic principles type question, and this is related to a specific component called the 555 timer, which you don't necessarily need to know about, but we have a schematic diagram, and then we have a breadboard layout here, and so I'll be answering this question. So a student uses the astable circuit shown in figure 2A below as part of a project. There's the diagram. We can see a few bits and pieces there. To test if the circuit meets the specification, the student constructs the circuit on a prototype board. Okay, so here's our breadboard or prototype board, and this is how they're shown to have connected it. So we've got our power supply there and there, 10 nanofarad capacitor connecting 0 volts to this breadboard track, which is then connecting to 5 volts, to pin 5 rather. So you can see that that's that one there. Okay. So what we need to do now is draw into the figure in the correct positions the 12k resistor, the 30k resistor, the 0.1 microfarad capacitor, and any connecting wires needed to make it work. So I'm just going to start with the 12k resistor first. So the 12k resistor is going to be connecting the positive supply, so it's going to be along this rail along the top here, so somewhere along here, and that's going to be connecting to pin 7. So there's pin 7. So draw a resistor and connect it something like that, and we should write 12k next to it. The 30k is connecting pin 7 to either 6 or 2. So I could do something like this. Okay, so you can see that 6 is connected to 2 with this wire, or this set of wires here. So I can take advantage of that connection there. Put a resistor there like that, connecting pin 7. to pin 6 and 2. That's my 30k ohm resistor there. The 0.1 microfarad capacitor is then connecting pin 6 or 2 to our 0 volt connection. So pin 2 is here. So let's put in our capacitor. And that's connecting to there. And it's 0.1 microfarads. And just to check to make sure any wires, we're not missing any wires. So pin 8 on this diagram is not connected. That's connecting to positive. You can see pin 8 here. I can connect that up to positive. And what else are we missing? Pin 4, that's also connecting to positive, so that's right. We've looked at pin 7, 2 and 6. Pin 1, that needs to connect to 0 volts, so let's connect that down there now, like so. And establish that pin 5 is connected with a 10 nano capacitor. And the output is connected there. Okay. Let's go into the next part of this question. The student needs to calculate the power consumed by the circuit. So this is a another basic principles type question. Okay, so we've got a power supply, we've got an ammeter and a voltmeter, and here's our circuit. So draw how the connections should be made. All right, so if we want to measure the current, this ammeter, that needs to go in series with our circuit somewhere. Now it doesn't really matter, I could put it in series with the positive connections here, which is what I'll do because it seems to be in line with it. But I could have had that in onto the 0 volt connections just as easily. I'll connect the 0 volt on there like so. And in order to measure the voltage, we just connect the voltmeter across the 0 volt and the positive supply, like so. Okay, so part 2 of question B there is talking about the readings we get. So we get 8.9 volts and 5.1 milliamps. The power consumed by the circuit goes by the formula P equals V times I. And now we just substitute in our values. 8.9 volts times 5.1 milliamps, which is really 5.1 divided by 1,000. So 8.9 times 5.1 divided by 1,000 is equal to, using the calculator, 0.04539, and that will be in watts, which I'm just going to use 3 significant figures, and I'm going to use a more appropriate unit here. So 0.045 is going to be 45 milli. So that's 45.4 milliwatts. A bit clearer, that's a 4 there. So 45.4 milliwatts would be the power used by this. Okay, so this is a power supply type question, which is related to the basic principles. So we've got a technician is designed a DC power supply. Figure below shows part of the circuit that uses a step-down transformer and a bridge full wave rectifier. Okay. So the key point that we recognise with a bridge rectifier is that the diodes connecting to the outputs will point. So we've got 2 diodes. One will go here to there, here to here, one will go here to here, and they're going to be pointing in the same direction. Okay, so that's coming later on there, I think. State the name of the component labelled A in there. So this is in line with our this thing here. This is a transformer, and that is a symbol for a fuse. So draw onto figure 3 the 3 remaining diodes correctly connected to complete the rectifier bridge. So, like I mentioned before, these 2 diodes need to be in the same direction. So when this is positive, this will be negative, so we want this to conduct, but this one not to. Likewise, when this is positive, we don't want this one to conduct, so the diode here will have to be in that direction. And this one, so when this is negative, we want the conduction to go that way, but not that way. So this will be positive, so we want that to go like that. Okay. The transformer produces an output of 12 volt RMS. Now we haven't covered RMS just yet, so I'm going to skip that question. Okay, part C, explain 2 important features of a transformer to help improve electrical safety. So there's the 2 features that this is going to be talking about. Is we have a 240 volts on the input there. Now that's a lethal voltage. So its input is going to be a lethal voltage, but its output is going to be something much safer to work with, 12 volts. So it reduces the voltage to safe levels. That's one of them. The other one that's probably a little bit less obvious here is that this input conductor here is electrically separate from the output conductor on this side. So the input here and the output here aren't electrically connected. They're magnetically connected, but they're not electrically connected. And that means we have a isolation. So if a fault were to occur somewhere on here, then the transformer would isolate this circuit from that fault and protect a user from being electrocuted. So the isolation between primary and secondary coils in the transformer. Okay, part D. Long question, this one. Technician decides to add an LED with a protective resistor to the DC output to show the power supply is on. So draw on the diagram, the LED and a resistor to show the power supply is on. Okay, so here's our DC output on this side. So this is the positive. Now it doesn't matter which order you put the LED resistor in. You can have the resistor, then the LED. There's my LED there, and my protective resistor. Why do we need that resistor there? The LED would overload without it. So the LED can only take about 2 volts of forward voltage. So it can only drop about 2 volts. So the resistor will drop the remaining voltage. Limiting the current. preventing it from burning out. Preventing it from failure. Okay, so this is a function block diagram type question. A street lamp is turned on when it gets dark, but is turned off at midnight to save energy. The system diagram, function block diagram, sometimes called, or IPO, input processor output function block diagram, is shown below. So the two systems that are inputs are going to be, they're on the left hand side of this diagram. So there's going to be a light sensor and a timer. Okay, so these are our inputs on this side. And you can see that there's nothing leading into them, which is what makes them the input. The subsystem that is an output is the only one that doesn't have anything coming out of it, and that's this lamp. We might find an AND gate in this logic block. Yeah, so an AND gate is a logic circuit, and they haven't specified what the logic is, but I would suspect there might be an AND gate in there. The light pendant resistor, well, we might find that in our light sensor. That's what they're used for. Transistor and an electromagnetic relay. So we use a transistor and a relay as a buffering circuit where we take a small control signal to switch a large current or maybe even a high voltage circuit. And so we would find that on the output of the logic circuit, but before the lamp. So this would be the driver circuit. Okay, now we haven't covered this. The op-amp would be found in the comparator. So I'll just put it across with that because we haven't covered that yet. Name the subsystem that produces an analog output. That's going to be not related to what we're talking about. However, yeah, no, we'll leave that for the minute. Is a digital process. So that would be the logic gate. So logic circuits are digital. So and okay, we haven't covered ADCs really either. Okay, question 5. From experience working with circuits on breadboard and PCB, describe one or more methods that we can identify each of a dry joint or a cold solder joint. So we can use a visual inspection. Or measure resistance or voltage. Both of those methods will help you. So sometimes a dry joint is hard to see. And so if there was a dry solder, basically what that means is that the solder hasn't connected the two metal components together properly. So we might see that as a voltage that shouldn't, or a voltage level that it should not be. So it might be 0 volts, but it should be 2 volts or something like that. Depending on the components connected to it, depends whether we'd be able to measure resistance effectively or not. An open track, we can use a continuity tester. Or if you don't have one of those, we can use a multimeter measuring resistance. So measuring resistance would give low resistance would be a good track. A high resistance, so anything more than about 10 ohms is probably going to have a problem with the track. A potential short circuit between the components, we can visually inspect it. Or we can also measure resistance. So low resistance in this case would mean a short circuit. So how could we identify a component that may overheat or has already overheated? So already overheated, well, you can see that usually. So visual inspection, or sometimes you can smell them. So if you smell what smells like burning paint or something like that, chances are it has overheated. And I don't know about may overheat, so it's probably smoking as well. Smoke or scorch marks. Okay, so you can see those. Not sure about an alternative to those, and certainly not about one that may overheat. Maybe you might know low resistor value with a low power rating. That's the only one I can think of where we might be able to predict that it will overheat. So if I see a 100 ohm resistor and it's going across 9 volts or something like that, and it's only a little quarter of a watt resistor, be pretty sure that that one's going to get smoked eventually. So might be able to predict that one. Okay, question 6. Electronic circuit design software, a bit like Circuit Wizard, can be used to simulate the behaviour of circuits. What operations or tools in Circuit Wizard or similar electronic simulation allow input and output voltages to be displayed? So what you can do here is you can add meters or probes. So the probes in Circuit Wizard allow you to monitor the voltage at a particular point and graph it over time as well. So the meters can be a bit difficult to add in, so or cumbersome. But that's okay. The probes, well, the probes really don't have a limitation. You can show the voltage. It doesn't give you precise values necessarily, so you might have to read that off. So probes don't show the number, but rather a graph. So Circuit Wizard has some limitations in representing the behaviour, so when simulating. So circuits like high frequency may not simulate properly. just by the virtue of the way the simulation works. It sort of looks at it in chunks of time. It's not a continuous thing. And so high frequency circuits, so if we had a circuit like an astable that was switching faster than the simulation step time, then it may not simulate properly. The other thing is that these components are ideal or perfect. Yeah. So may not give an accurate representation. In some cases. I'll add another answer in there in that, what was I going to say with that? Oh, talking about inputs here. So realistic can be difficult. To simulate. So an example of this might be I've got an audio circuit for music, and I might want to simulate my amplifier circuit or my audio circuit. I can simulate that with signals of some sorts, but to actually put real music in is a bit difficult. Okay, so it looks like we've got ourselves another function block diagram type question. By the looks of it, there may be some analog stuff in here, so let's see if it's a relative. No, that's not really relative to what we're talking about yet. Okay. No, none of those. Okay, that's it for part B. I'll do the other parts in a different video.